So this is we are calculating the partial derivative continuity. So if partial derivatives are continuous along x-axis, partial derivative is continuous along y-axis, then it is considered as differentiable in a particular region where partial derivative are continuous. If partial derivative are continuous in a particular region, then it is considered as differentiable, but not reverse. If something is differentiable, then not required that partial derivative would be continuous. If something is differentiable, any function is differentiable in a region, guaranteed that partial derivative would exist, but they are continuous or not, that is not guaranteed. But if partial derivative are continuous, then it is guaranteed that it is differentiable. So we will just need to check. So this is what we are calculating. So fxy equal to ln x square plus y square. This is the equation. So if z equal to fxy, the dz by dx or fxxy equal to 1 by x square plus y square, where where now again we will differentiate x square plus y square, that will come as 2x by x square plus y square. So partial derivative along x-axis will come as 2x by x square plus y square. So dz by dy will come as 2y x square plus y square. Now from the first glance, okay, it looks like the numerator and denominator, that is 2x by x square plus y square are continuous. So this looks continuous in a region. Okay, let's go for the continuity testing. So that is required. So for continuity testing, at any point, we take the point first. So I am testing the continuity at point A comma B. So now we have fxxy equal to 2x by x square plus y square. That is differentiated from ln log x square plus y square. 2x by x square plus y square. So fxxy equal to 2x by x square plus y square. If I am calculating at a comma b, then it will come as 2a square plus b square. Now at a comma b, when a and b are 0, it is 0. So fx 0 comma 0 is 0 because numerator is 0. Now we will calculate at any distance delta x delta y, or if I say fx xy, when xy tends to a comma b, then fxxy also should be limited to fx a comma b. This is the limiting. If xy goes near a comma b, then fxxy should also go near fx a comma b. If I take a small distance from a comma b, that is h in x direction and k in y direction, or delta x delta y, then fx a plus h b plus k equal to, okay, equal to 2a plus h divided by a plus h whole square b plus k whole square. Now h and k, they are limiting to 0. Okay, so if a comma b is a point, okay, in this region, if a comma b is a point, then in this direction h and in this direction k. So in finitesimal small, we have taken h and k. If h and k are small in x direction, y direction, if fx ab is partial derivative along x-axis at point a comma b, then fx a plus h b plus k is partial derivative along x-axis at point a plus h and b plus k. When h and k, they are limiting to 0 0 0 comma 0, then fx a plus h b plus k should be limiting to fx a comma b. That is the idea. Now fx a plus h b plus k equal to a plus h, 2a plus h, because it is 2x by x square plus y square, 2a plus h divided by a plus h whole square plus b plus k whole square. Now if a comma b is 0, then it will come as 2h divided by h square plus k square. Now since it is partial, now if we are considering, now we are, this is a comma b, we are approaching from a point that is a plus h and b plus k towards a comma b. If now suppose that now I'll test the continuity along x-axis first. I'll test the continuity along x-axis first. If I want to test the continuity at x-axis first, then k would be 0. We'll take k as 0. That is the case. Then it will be 2h by h square, that is 2 by h. So if fx a plus h b plus k, where h and k tends to 0 and a comma b is 0 comma 0, then it is coming at 2 by h. 2 by h, eh, we remember that fx a comma b is 0 if a comma b is 0. So the partial derivative along x-axis at origin is 0. Now, if I go small distance h in x direction and a small distance k in y direction where k is 0, then it is coming as 2h. So the fx a plus h b plus k, where hk tends to 0, this is directly proportional to 1 by h or inversely proportional to h. If h is becoming 0, then fx a plus h b plus k is going to infinity, whereas it should go to 0. Means that is the idea, right? If this is a comma b and if this is h along x-axis, if h is approaching towards a comma b, then the value of fx a plus h b plus k should be 0, because it should be equal to f a comma b, fx a comma b, or fx 0 comma 0. Fx xy is the partial derivative along x-axis. So, but when now we calculated fx a plus h b plus k equal to 2 by x, means it is directly proportional to 1 by x or inversely proportional to x to h. So if h is moving towards a comma b, then the value of fx a plus h b plus k is going to infinity. It should go to 0 as per the limiting fundamental. So the partial derivative along x-axis is not continuous at origin. At origin, when the partial derivative should be 0, here partial derivative is 1 of 2 by h. If h is going towards becoming 0, then partial derivative is going to infinity. So the partial derivative, that is 2x of ln log x square plus y square along x-axis, is 2x by x square plus y square. And partial derivative has value 0 at origin, whereas if I calculate the continuity, for that I am calculating the limiting where the h and k are infinitesimally away from a comma b or from origin in x direction or y direction, and if I take k as constant and 0, then it is inversely proportional to h. So if h tends to 0, then partial derivative along x-axis for the continuity test, the limit is going towards infinity. So if partial derivative is not continuous at origin. So this is what we calculated now. So what we are trying to show, that if partial, we are trying to, first we know that if partial derivative is continuous along x-axis and y-axis, then certainly it is differentiable. But since partial derivative are not, they are calculated function of x and y, but they are not continuous. Okay, if fx xy is not continuous at origin, fy xy, that is 2y x square plus y square, that is not continuous at origin either. Okay, so in that case it is not differentiable at origin. Now let's see at any other point, that is 1 comma 1. If it is 1 comma 1, then fx 1 plus h 1 plus k equal to 2 1 plus h divided by 1 plus h whole square 1 plus k whole square. Same way, we will take now k as 0. So from the x-axis side, we will approach towards a point that is 1 comma 1. Earlier we were approaching towards 0 comma 0. Let's see what is fx 1 comma 1. That is 2a divided by a square plus b square. That is 2 by 2. That will come as 1. So at fx, the partial derivative rate of change along x-axis, partial derivative fx xy at 1 comma 1 is 1. Now let's take fx a plus h b plus k, where a comma b is 1 comma 1. That will come as 1 plus h, 2 into 1 plus h, 1 plus h whole square into 1 plus k whole square. If I take only x-axis and approach in x-axis keeping the y constant at k equal to 0, that will come as 2 1 plus 2 into 1 plus h divided by 1 plus h whole square plus 1. Okay, so that is 2 into 1 plus h divided by 1 plus h. 2 into 1 plus h divided by 1 plus h whole square plus 1 plus k whole square. So f1 plus h, fx1 plus h, 1 plus k equal to 2 1 plus h divided by 1 plus h whole square plus 1 plus k whole square. Now, if we make k as 0, okay, so only x-axis we are calculating, then it will come as 2 1 plus h divided by 1 plus h whole square plus 1. Okay. Now 2 into 1 plus h divided by 1 plus h whole square plus 1. If h tends to 0, then it will come as 2 by 2. That is 1. So this is what is expected. So if I calculate at point a comma 1 comma 1, if I calculate at point 1 comma 1, then fx1 plus h1 plus k equal to 2 into 1 plus h divided by 1 plus h whole square plus 1 plus k whole square. If I take calculate only in the x direction, keeping y as constant, and that is 0, so k equal to 0, that will be 2 into 1 plus h divided by 1 plus h whole square plus 1 plus 0 whole square. So if h tends to 0, it will become 2 by 2, that is 1. So it is continuous in all the regions. If it is continuous at 1 comma 1, then it is continuous at all the regions. Now it is only not continuous at origin. Otherwise, the partial derivative along x-axis is continuous along the all regions. Same thing we can calculate for the same stuff we can calculate for the y-axis. For the now we calculated partial derivative along x-axis that is continuous for the whole region except origin. Same way, we can calculate partial derivative along y-axis, that is 2y by x square plus y square. It is continuous in the full region except the origin. Now what we see, if we have a function fxy equal to x square plus y square, fxy equal to log ln x square plus y square, whose partial derivatives are 2x by x square plus y square, 2y x square plus y square, then both partial derivatives are continuous in the full region except at the origin. Now, as per the fundamental, if partial derivative is continuous in both a region, then it is, since it is continuous in both regions, then at any point the partial derivatives, both partial derivative, they constant. The idea is that partial derivative, both partial derivative should exist at any point. That's why we took the tangential surface at the beginning. Now what we see that if there are two conditions. So one is if function is continuous in a region, and then or it is continuous at a point in a region, and at that point it is partial derivative also exists at that point, both partial derivative, then we can calculate the continued differentiability at that point by calculating the relative error, where relative error, the limit should be 0 when we approach to the point. The relative error to the point where we are calculating the continuity and partial derivative, relative error limiting to that point should be 0. If that is the case, that it is continuous at that point and both partial derivative exist and relative error at that point is 0, then it is differentiable. This is what we see one case. Next case, the idea here is that even if we have partial, now if we have we have a differentiability at any point in the region, and differentiability for all the points in the region, we see that differentiability exists, then function is differentiable for the full region. If this point we see it is differentiable, and like this at all points it is differentiable in a particular region, then function is considered as differentiable in that region, full region. Okay, this is one way we calculated that differentiability exists. In other way, the idea is that when we have partial derivatives available, okay, then both partial derivative we have to take into account in one go. That's why we came with local linearity and tangential surface. That is the concept. Now, when we have to take both the partial derivative in one go, then another idea, and we are taking the continuity of the function, then if partial derivatives are continuous along x-axis and y-axis full in a region, then at any point, if we take in the region, then both partial derivatives are coming into the picture. If that is the case, then at that point it is differentiable. No need to calculate the continuity of the function. Just calculate the partial derivative. And if it is coming as function of x and y, then partial derivative is x comma y, then partial derivative can be checked for the continuity. If partial derivative is continuous along x-axis and y-axis, then at any point in the region, okay, the differentiability exists, but not the other way. If differentiability exists, then there is no warranty that partial derivative would exist, but it is continuous in that way. But so then it is more stringent. The partial derivative is continuous is more stringent than differentiability. Whereas if continuity of the function exists and both partial derivative exist at a point, then there is no warranty that it will be differentiable. That we saw in a case where fxy equal to x to the power 1 by 3, y to the power 1 by 3. Whereas if fxy equal to xy divided by x square plus y square, where it is 0 at 0 0 and not 0 at if it is not 0 0. In that case, we saw that continuity does not exist, but both partial derivative exist. So it is not differentiable. Okay, so these are the cases like in the cone case, fxy equal to x square plus y square square root. Here we saw that the continuity exists, but it is partial derivative do not exist, so not differentiable. Okay, whereas fxy equal to x square plus h square, that is paraboloid, there differentiability and both partial derivative and continuity exist, so it is differentiable. Now, if we come to partial derivative should be continuous, then we have fxy equal to log x square plus y square. There we saw except origin, partial derivative is continuous along the region. Okay, if it is continuous along the region, then 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 it is differentiable along the region except 0 comma 0 where partial derivative is not. If partial derivative exists but it is not continuous, if it is not continuous, then it is not differentiable at that point. So that is the concept that we saw. Okay, so we will see more on it, like we'll calculate the kind of differentiability actually at 0 comma 0, and then we'll end this discussion basic calculus, and then we'll proceed on kind of local minima maxima and high profile integration. So that will